in the previous lecture we have proved the Hahn-Banach theorem. We have proved it in general linear spaces. We did not assume any structure like metric or norm. Let me start this lecture with a specific form of Hahn-Banach theorem, the corollary of the general result for the normed linear spaces. So let X be a normed linear space and Y be its subspace. Now, if we consider a bounded linear functional on Y, then we can extend it to the whole space X, preserving the norm. So there exists a bounded linear functional on X such that f bar of Y equals to f of Y for every point from the subspace, and the norm of f bar equals to the norm of f. So we will apply the Hahn-Banach theorem from the previous lecture for a specific form of a functional P. So consider a functional P of x, which equals to the norm of x times the norm of f. Well, it's easy to see that this functional is positively homogeneous and subadditive. This is just the property of the norm. So we also have that an absolute value of f of y is less than or equal to the norm of y times the norm of f by the definition of the norm of a function. And this holds for any y from y. So the functional, well, we have even this one. So the functional f is in fact dominated by the functional p on a subspace. So by Hahn-Banach theorem, it can be extended to the whole space. There exists a functional f bar on x, a bounded linear functional. Well, technically speaking, from that result, we don't know whether it's bounded or not. So there exists a functional, a linear functional on x such that it extends f and it is dominated by p. This inequality in particular tells us that this new functional is a bounded linear functional. Well, the linearity follows from the Hahn-Banach theorem, so this inequality tells us that it is bounded. And what is left to prove that the norm of f bar equals to the norm of f. We have f of x, I just copied this. And also, if instead of x I will write minus x, then this minus 1 can be factored out of f bar by linearity. Then I can multiply the both sides by minus 1 and the inequality will be reversed. So by doing this, I get the estimate from below, which is minus norm of minus x times f. So this second estimate from below, we get it by linearity of f bar. Do you want me to explain it?
Yes.
Since f bar of minus x is less than or equal to the norm of minus x times the norm of f. I just use this inequality for minus x, it holds for any x. And then we have this one, so the functional is linear. And now if I multiply both sides by minus 1, I get exactly the estimate from below. Using this double inequality, we can conclude that the absolute value of f bar of x is less than or equal to norm x times norm f. In particular, it means that the norm of f bar is less than or equal to the norm of x. Oh, sorry, the norm of f. To prove the equality, we will prove the converse inequality. The norm of f bar, by definition, equals to the supremum of the absolute value of f bar of x over all x's from x, say such that the norm of x is 1. Now, instead of taking the supremum over the whole x, I will take the supremum over the subspace y, which makes this supremum, which provides the estimate from below. But now, this x belongs to y, and f bar and f coincide on y. So what we have here is just f of x, and we're taking supremum over y, so which is the norm of x. Sorry, the norm of f. So this proves the estimate from below, and so the norms coincide. Let me state a couple of more corollaries from the general result from the previous lecture. Let x be a non-linear space. The first statement, the first assertion. For every x from x, there exists a bounded linear functional such that f of x equals to the norm of x. The norm of f equals to 1. In particular, this result implies that for any non-linear space, the dual space of all bounded linear functionals on that space is not empty. The second assertion gives us a formula to compute the norm of an element. It can be computed as a supremum of the absolute value of f of x, where the supremum is taken over all bounded linear functionals on x of norm 1. And well, of course, this holds for every x. And let me state one more. For any two distinct points from the space, there exists a bounded linear functional which takes the different values on these 2 points. So in this case, we will say that the space x star separates points. Today we consider another type of Hahn-Banach theorem, which is generally called geometric form of Hahn-Banach theorem. So throughout this lecture, we suppose that X is a linear space over reals. And let us consider a subset K of X such that K is convex and K has at least one interior point. Well, over here I just wrote that X is a linear space, so I don't want to assume that there is any norm or metric on this space, but over here I'm speaking about the interior point. If you remember, we have defined a point to be interior if it lies in the set together with some ball around it. But the point is that when we define a ball, we need a metric. So we define the distance. So let me now write down the definition of the interior point without metric. Without loss of generality, we can assume that this interior point is 0. Why is it so? Well, if K does not contain 0, 0 is not an interior point. But it just has some interior point. Let's just shift it to 0 and we're done. So we have used, you have used this trick in the school geometry. When, for instance, you just have some point, and for convenience of computations, you draw a Cartesian coordinate through this point and say this will be our 0. That's what we do here. Without loss of generality. Zero is an interior point. Of K. So now we have a convex set K such that 0 is the interior point of K. And for such set K, let us define a functional P sub K of X to be an infimum of all A such that A is greater than or equal to 0, just strictly greater than 0, and X over A belongs to K. And we define this functional on the whole space X. Well, first of all, since 0 belongs to the set K without loss of generality, this functional pk is well defined, so it is always finite. Let us consider a simple example to see how this functional pk works. Let k be an interval minus 1, 1, well, in the real line. What is then p sub k of 0? So this is the definition. We take any scalar, well in our case it's a real number, so we take any positive real number, divide an element x by this number, and compute the infimum over all such a, such that this expression belongs to k. So in our case, a is positive, and over here we have 0 over a belongs to k. So in fact, for any positive scalar, for any positive real number, 0 over a does belong to k. So when we take in the infimum over all positive real numbers, what do we get? It's 0. Let us also compute pk of 1. So again, we take an infimum of all a positive such that 1 on a belongs to k. So if a is strictly less than 1, then 1 over a does not belong to k. But for any a which is greater than or equal to 1, it does. So in fact we are taking infimum over all a greater than or equal to 1, which is 1. What will be the value of this functional pk at minus 1? Pk of minus 1. Again, it's an infimum of all a positive such that minus 1 over a belongs to k. So let me write it like this. Infimum over all a such that minus 1 over a is less than or equal to 1 and greater than or equal to minus 1. Or, so it is 1 as well. And so, this is how it works. This functional pk, which we define, it turns out that this functional is positively homogeneous and some additive. So let's prove this. The positive homogeneity follows directly from the definition, from this formula. Let us prove that this functional is subadditive. So let x and y be 2 points from k, and a and b be positive real numbers, such that x over a and y over b belongs to k. Since k is convex, it contains an interval between these 2 points. The general form of the interval is this one. For every value of lambda between 0 and 1, this linear combination belongs to the set K. And let me now choose a specific value of lambda. So let us take lambda to be a over a plus b. Let me substitute this value of lambda into the left-hand side of this expression. Over here we have a and a cancel each other out, so we have x over a plus b. 1 minus lambda equals to b over a plus b. So over here b and b cancel each other out, so it will be y plus y over a plus b, which is x plus y over a plus b, and we know that a belongs to k. By the definition of the functional pk, we can conclude that pk of x plus y less than or equal to a plus b. On the other hand, p sub k of x plus y. So what I will do now is I will take this inequality and take the infimum of both sides of it. And the infimum will be over all a and b which are positive, and such that x over a, y over b belongs to k. So I just taken this inequality and applied this infimum to both sides of it. The left-hand side does not depend neither depend on a or b, So we just have this expression. Even in the way it is written, this infimum is taken separately in A and B, so we can split it. And the first summand is nothing but pk of x, and the second one pk of y, which proves that the functional pk is sublinear. And we're done. Let us state a proposition about the values of the functional p sub k. So let k from our linear space X be convex and has at least one interior point. We have first pk of x is less than or equal to 1 for every point x from k. The second part tells us that the value of this functional is strictly less than 1 if and only if x is an interior point of k. So this is an exercise for you to prove. What is more interesting about this result is that the converse of this statement holds. We already know that we already proved that p sub k is a positively homogeneous and subadditive functional. Now let us start with any positively homogeneous and subadditive functional. First, the set of all x's such that p of x is less than or equal to 1 is convex the second statement is that the set of all x's from x such that p of x is strictly less than 1 is convex and contains 0 as an interior point. Before we will go further to some two other variants of Hahn-Banach theorem, let me start with a very simple example. So let me consider a linear functional on R3. Let f be a linear functional on R3 such that f of x, well, x is a vector, equals to ax1 plus bx2 plus cx3. Or rather, let's go with a1, a2, and a3. Then equation f of x equals to c geometrically describes a plane in R3. And this plane splits R3 into 3 sets. The plane itself, the points below the plane, and the points above the plane. What is interesting in this construction is that it is generalizable to arbitrary linear space and to arbitrary linear functional. We are still in our linear space X throughout the whole of this lecture. And let us consider a linear functional on X. and let C be a constant. And now let us call a set of all x's from x such that f of x equals to constant. So in that example in R3 we call it a plane. Well, this is a generalization, so let us call it a hyperplane. As in this example in R3, the whole linear space X is split into sets. And we have that X equals to all points from X such that f of X is less than C union with the hyperplane and union with all the points lie above the hyperplane. And now let us state our first result, which is the geometric form of the Hahn-Banach theorem. It is typically it is called the separation theorem. So let us take a set K to be convex, non-empty, and open. Now, if we take a point which does not belong to K, then this point can be separated from K by hyperplane. That is, there exists a linear functional on X and a constant C such that f of y at that point equals to C and f of x is strictly less than C for any x from K. Well, if we go back to our example in R3, it tells us that if we have an open, convex and open set, at the point which does not belong to this set, then through this point we can draw a plane such that the set K lies below this plane. So this is the geometric meaning of this result. Okay, let's prove. Well, first of all, let us assume that 0 belongs to our set K. If not, we just shift the whole space to make 0 belong to K. Then we can consider the functional P sub K. Well, since K is open, which means that any point in K is an interior point, then P sub K of x is strictly less than 1 for any x from K. Now let's take this point y, which does not belong to K, consider its span, and define a linear functional on that one-dimensional space, subspace. Define f on the span of y by setting Any point from the span of y is just a scalar multiple of y. So it is of the form lambda y. And we set f to be lambda. Well, it is easy to see that the functional f is linear on span of y. What I claim is that f of x is less than p sub k of x for any x from the span of y. So let's prove this. So first of all, if x is from the span of y, x equals to lambda y. Well, let us consider two cases. The first case is that lambda is less than or equal to 0. Then f of x equals to lambda by definition, which is less than or equal to 0. But the functional p sub k is always non-negative because it's an infimum over the positive integers. So in this case, we proved that f is dominated by pk. Let us now consider the case of negative lambda. If lambda is negative, then we have that p sub k of y is greater than or equal to 1, since y does not belong to k. Yes, if it's greater. So we have this inequality, and p sub k of x equals then to p sub k of lambda y. Lambda is positive and p sub k is positively homogeneous. So it equals to lambda p sub k of y, which is greater than or equal to 1. Almost correct. Lambda. Much better. So this one is estimated by 1 from below, so this one is estimated by lambda. And by definition of x, by definition of f, it equals to f of lambda y, which is f of x. So we have proved in fact that f is dominated by pk on this subspace. So by Hahn-Banach theorem we can extend the functional f to the whole space, preserving the dominance. Let me go with f bar on x, such that f bar of x less than or equal to p sub k of x for any x from x. In particular, we have that f bar of x strictly less than 1 for any x from k, since any point of k is interior point, k is open by the previous result. But also by definition of f bar, it coincides with f, so its value at y equals to 1. So the value of f bar at the point is 1, and the value at any point from the set K is strictly less than 1, and we're done. Let me state a corollary of this theorem. So let K be a convex set with at least one interior point. So we drop off the condition for the set K to be open. So it can be any set, we just want that it has at least one interior point. And also let Y be a point which does not belong to K. Then there exists a linear functional on X such that f of X less than or equal to f of Y for any point X from K. Let me now state one more separation theorem. So in the first separation theorem, we separated a point and a set. In the second version of it, we will separate two sets. So let A and B be two sets from our linear space. So what we want from them? We want them be disjoint, which is kind of natural. If they do intersect, then of course we cannot separate them. So let these two sets be disjoint, convex, and at least one of them has at least one interior point. Then there exists a linear functional f on X and a real number C such that f of A less than or equal to C less than or equal to f of B for any A from A and B from B. Let's prove this. Let us consider the set K. Every element of the set K is of the form A minus B for some A from A and some B from B. Well, it's not difficult to see, and this is an exercise for you, that K is convex. K is convex. K has at least one interior point. And 0 does not belong to K. So all these three conditions are guaranteed. The convexity is guaranteed by the convexity of A and B. That it has at least one interior point is guaranteed. That either A or B has at least one interior point. And the fact that 0 does not belong to K is guaranteed by the fact that A and B are disjoint. Well, indeed, if they do intersect, they have a common point. And so we can find A from A and B from B which equal to each other, and so A minus B will be 0. Since the sets are disjoint, there is no 0 in K. And now we will use that corollary, well, for K being K and for Y being 0. By previous corollary, there exists a linear functional f on x such that f of x less than or equal to f of 0. But the functional is linear, so what is the value of f at 0? It is 0 for any x from k. By definition of k, any x from k is of the point a, is of the form a minus b. Then what we have is that f of a minus b is less than or equal to 0. But f is a linear functional, so we can split it and rearrange. Or f of a less than or equal to f of b for any a from a and b from b. We are almost done. So we proved that f of a is less than or equal to f of b for any a and b. What is left is to squeeze a constant in between of them. So let us take C to be a supremum of f of a for any a from a. Or equivalently, we can take an infimum of f of b for any b from b. Hence, f of a less than or equal to the supremum over all a from a, which is C. But f of a is less than or equal to f of b for any a and b. So supremum of f of a is also less than or equal to than f of b. And we're done.